Correcting the proximity effect in nanophotonic phase arrays. Most of the VR and AR headsets available today rely on a stereoscopic vision for depth cues. They usually suffer from a limited number of focal planes, which leads to vergence accommodation conflicts. In this case, the brain thinks that you are focusing at one distance, but the muscles in the eyes think otherwise. The VAC is known to be a major cause of discomfort in VR and AR. Varifocal displays and live field displays offer a wider range of focal distances. However, they both have disadvantages, such as being bulky or being limited by optical diffraction. Holographic displays, on the other hand, recreate the optical wavefront of a scene, naturally addressing the vergence accommodation conflicts. Additionally, holographic displays are based on optical diffraction. Smaller pixel pitch would only improve their quality. The holographic displays recreate the wavefront by modulating the amplitude and/or phase of light waves. Phase modulation is more common. The liquid crystal on silicon spatial light modulators, or SLMs, have been the most widely used phase modulators for holographic displays. They modulate the phase by adjusting the refractive index of the liquid crystal with different levels of voltage. There are no SLMs with very high resolution and good refresh rate up to a few hundred Hz. Nanophotonic phase arrays, or NPAs, are phase arrays operating at optical wavelengths. Recent years have seen them being used for phase modulation in holographic displays, notably the 2013 Nature paper from Professor Wall's team from MIT. The biggest advantages of the NPAs in this area are their integrated light source and the super fast refresh rates. A laser can be directly coupled into the NPA and distributed to antennas to be emitted into free space via optical circuit. Also, our simulation shows that the similarly modulated NPA can complete the phase modulation cycle in 10 microseconds, suggesting a refresh rate of up to 100 kHz. The phase modulation in our NPA is based on thermal optics. Temperature adjusts the refractive index and therefore the phase. The phase at the pixel is linear to its temperature above the ambient. It is therefore important to note that the temperature must be non-negative in the hologram calculation because there is no cooling capability. This thermal modulation leads to the thermal proximity effect, which put simply is the phenomenon where heating one pixel affects the temperature of nearby pixels. We model the thermal proximity effect as a Gaussian convolution. The severity of the proximity effect is represented by sigma. Larger sigma indicates more severe proximity effects. Our NPA design has sigma equal to 0.66 pixel. Other NPA designs may have different sigma values. The thermal proximity effect negatively impacts the phase modulation accuracy, degrading the quality of the formed imagery. It is therefore necessary to perform proximity effect correction, or PEC. We propose two PEC methods. The first is the iterative proximity effect correction, or IPEC. It is based on the well-known Gershberg-Sexton algorithm. We consider the Fourier hologram where the object plane is far enough from the hologram plane so that the propagation can be approximated with a Fourier transform. This does limit our method to holograms of 2D images, but we believe that this is a reasonable simplification for the first step on this topic. Our IPEC method replaces the source amplitude constraint in the GS algorithm with the equations highlighted in yellow. The phase of wavefront B is formed by applying the proximity effect to the corrected phase of wavefront A. The function P sub k inverse is the inverse process of the proximity effect, considering the non-negativity. To be precise, P sub k and P sub k inverse should apply to the temperature. But since the relationship between the temperature and the phase is linear, we directly use the phase for simplicity. Since the proximity effect is a convolution, we can write the correction as a deconvolution to find the non-negative phase that minimizes the difference between convolution result and the desired phase. If the correction step is skipped, the IPEC method becomes very similar to the method in Gamaya et al. 2016. We refer to this method as the basic IPEC method and use it as the baseline to compare our methods to. The second method is the proximal PEC or PPEC method. In this method, we use the proximal algorithm to find the non-negative phase x that minimizes the residual g of x, which is the difference between the formed waveform intensity u of x under the proximity effect and the desired image I. To enforce the non-negative constraint, we add an indicator function c of x to the cost function to be minimized. C of x is 0 when all entries in x are non-negative and infinite otherwise. The proximal algorithm involves iteratively evaluating the proximal operator. We use the accelerated proximal algorithm, whose pseudocode is shown to the right. The most technical part is probably the derivation of the gradient of the function g. I'm going to omit the details here for time's sake, but it is available in the paper and the supplemental material. We carry out computational simulations to validate the effectiveness of the proposed methods. We implement our methods in MATLAB and run the simulations on an Intel 9900K CPU. We tested our methods on these datasets. In the PPEC methods, we terminate the iterations when the residual change is smaller than 0.1% for 10 consecutive iterations. From the qualitative results, the IPEC method performs much better than the basic IPEC method and is able to produce reasonable results. However, it is still not able to effectively correct the high levels of proximity effect. The PPEC method has the best correction effectiveness of all methods compared, and is the only method that can recover text-rich images when the proximity effect level is high. We also show the average image quality measured with SSIM degrades with the increasing amounts of proximity effect for the basic IPEC and the IPEC methods. The PPEC method retains the best image quality at all proximity effect levels tested. The PPEC method is also much faster than the IPEC method. The processing time generally increases with the proximity effect level. A few discussions. First, smaller pixel pitch, which is usually good for holographic displays, likely leads to higher proximity effect levels as the pixels are packed closer to each other. This makes the proximity effect correction more important, and the PPEC method is currently the only method that can effectively correct high levels of proximity effect. Second, there are several proximal algorithms to choose from. We end up using the accelerated proximal algorithm because this way we only need to evaluate the proximal operator of the indicator function c, which is easy. Another proximal algorithm, the ADMM algorithm, theoretically has faster convergence, but it will involve evaluating the proximal operators of both c and g. The function g is nonlinear, and evaluating its proximal operator is hard. In practice, we find the accelerated proximal algorithm to perform faster than the ADMM algorithm. There are some limitations to the MPA and to our PEC method. First, the MPA itself emits light, so it is hard for it to be used in diminished reality, like the SLM, to modify the wavefront of incoming light. Second, the initial phase plays a role in our PPEC method. In rare situations, a bad initial phase may cause the PPEC method to get into a local optima. Third, even though the PPEC method is able to effectively correct the proximity effect at the sigma values tested, it could not handle extremely high proximity effect levels, such as when the sigma is equal to 1.5 or 2 pixels. Going forward, we would like to study how to accelerate the PEC methods. Right now, it takes the PPEC method on average 6.61 seconds to process one color image of 100K pixels on the CPU. We expect massive parallelization and other specialized hardware for Fourier transforms to significantly improve the speed. Also, digital holographic displays truly shine in displaying 3D objects. To calculate 3D holograms, our one naive method is to divide the 3D object into a stack of images and calculate the holograms for each image at their respective depths and display them one at a time with time division multiplexing. To do this, we will need to adapt our PEC method for Fresnel holograms. Alternatively, we could look into how to correct the proximity effects in a hologram that captures the entire 3D scene. Thank you.